thank you for organizing this wonderful workshop seminar and give me an opportunity to speak as a first speaker of this seminar. Yes. First, let me introduce myself briefly. I'm a postdoc researcher in JAXA and working under Takuji-san. And I actually am joined to the EarthCARE community from 2 years ago, and just before the launch of the EarthCARE. And so I'm relatively new person in the long history of the EarthCARE. And before that time, I was a PhD student at Kyoto University, and I studied about the Diana cycle precipitation and orographic precipitation by using spaceborne radar, such as TRIM or onboard TRIM and GPM and CloudSat. And now I am get involved in EarthCARE team and mainly developing one of the developer of CPR Echo, and also I'm joining in the GPM latent heating product team. And my the main job in JAXA is the development of EarthCARE and GPM coincidence dataset, and I will talk about this topic at this presentation detail. Yes. So first of all, I'd like to introduce the particle motion inside cloud and precipitation. And precipitation is important in global water cycle and related to heating and reducing budget. And it is a dynamic and microphysical process within clouds remain one of the major unsolved problems. And in mainly precipitation systems are broadly classified into convective and stratiform systems. In convective system, it has associated with intense and narrow updraft, and it promotes formation of larger hydrogen meteors through rhyming and coalescence. And on the other hand, stratiform precipitation, it has mesoscale ascent above the melting layer, and it accompanies downward motion below the melting layer because of the evaporation. Through the ground-based Doppler radar measurements, the feature of the such kind of convective and stratiform system has studied, but there are substantially variable structures with geographic and environmental conditions, so satellite observation is important for understanding the global characteristics. So I'm using spaceborne radar measurements by GPM and EarthCARE. And GPM carries a dual frequency precipitation radar DPR, which has Ku and Ka band dual frequency radar, and also it has microwave imager GMI. And this is the observation example of DPR, and it can measure the three-dimensional structure of precipitation. And also we estimate some kind of latent heating in such kind of system. And EarthCARE launched in 2 years ago, and it continues the CloudSat W-band cloud radar observation, and with the world first measurement of Doppler velocity. And by using Doppler velocity, we can get information about vertical air motion for the first time in globally. So by combining these two observations, we now examine the vertical motion inside stratiform and cloud convective systems. This is the history of precipitation, spaceborne precipitation and cloud radar observation. And in CloudSat era, CloudSat and TRIM GPM coincidence dataset has developed by Dr. Jotak, and which has widely used for studies on ice microphysics or like rainfall, snowfall. And so I am now developing ASCII GPM coincidence dataset. And the dataset compiles the orbit crossing cases between ASCII and GPM within 15 minutes. And it is already publicly available through the JAXA website. And the dataset includes the coincidence section while preserving the original data structure. And it already have 1.5 year observations, and more. We already have 4,500 cases and more in future. This is the number of coincidence footprints in the global map. And the cases are concentrated around about 60-degree latitude, which is because of the orbital feature of the satellite. But we are now gradually archiving broader coverage, including the tropics. Here, I will, in this seminar, I will introduce my study on the I submitted to the published in the atmospheric measurement technique. And in this study, I mainly focus on the match-up analysis between ASCII CPR and GPM DPR. And right-hand side shows the vertical cross-section of radar reflectivity and the velocity of the ASCII, and also the KU band and K band radar reflectivity from GPM. And now I'm focusing on how the characteristics of vertical motion differ among the precipitation type, structiform or convective. And also I interested in the Doppler velocity measurement from CPR is consistent with the particle size distribution estimated by DPR. And because Doppler velocity is the sum of particle air motion and reflectivity weighted particle fall velocity VTZ, and VTZ is related to the particle size and property. And on the other hand, GPM DPR can, from the observation of DPR, we estimate number of concentration and the mean diameter of the raindrops and snowfall. So we can compare these to independent measurement. This is a case study of convective and stratiform system over United States. And when we focus on the stratiform precipitation in the right-hand side of the figure, the Doppler velocity shows clear contrast above and below the melting layer. And it is snowfall and rainfall. And we can, there's some attenuation in reflectivity observation in W band, but when we see the Doppler velocity, it can be still measured in the rain layers. In convective part, in the left side, there is a severe attenuation in W band, and also in some Ka band. And when we see the Doppler velocity, it suggests a more turbulent vertical air motion and strong wind shear and great micro physical variability such as gravel, hail. And difference in Doppler velocity above and below the 0 degrees unclear. Next, I will show some statistical analysis. And this is a two-dimensional histogram of radar reflectivity on x-axis and Doppler velocity on y-axis. And for each column shows a different temperature range, and left-hand side shows the colder and right-hand side shows the warmer temperature. And for upper level ice below -10 degree, CPR, the above panel shows the CPR radar reflectivity on x-axis, and bottom shows the Ku band radar reflectivity. And in W band measurements, CPR radar reflectivity increased with Doppler velocity, suggesting very CPR is sensitive to and the microphysical light precipitation or cloud ice particles. On the other hand, KUPR cannot observe such kind of light precipitation. So there is the observation concentrated around here. But when we focus on the grown snow or rain, CPR reflectivity reaches saturation due to attenuation or Mie effect. So Ku band measurement.
Hello. You said my brain doesn't want to listen to.
Ku band measurement with
you were talking, okay.
is we can see the Ku band radar reflectivity increase with Doppler measurement. And now we focus on the radar reflectivity in Ku band and Doppler velocity. And next, we categorized convective and stratiform precipitation. And we classified deep clouds into two types. First, stratiform and convective according to GPM-DPR level 2 algorithm. And in GPM-DPR algorithm, each footprint are categorized into stratiform or convective according to special patterns of radar reflectivity, and such as right band and horizontal peakness. And in addition, we categorized the convective part further in two types, and according to whether DPR echo extends above upper level. And right-hand side shows the reflectivity on x-axis and temperature on y-axis. And this shows different feature among the different types. And especially we focus on the deep convective type, the distribution is more variable and than stratiform type. And tall one and moderate one shows a different feature above the melting layer, and splitting into two different ways. And again, for the upper level ice clouds, CPR increase with temperature, but in grown snow and rain, CPR reaches saturation and gets lower because of the attenuation. But when we make a similar figure using Doppler velocity, Doppler velocity in rain layers stays roughly around 4 meters per second, and this indicates that Doppler velocity measurement less affected by attenuation, and we can get information on rain or heavy snowfall. This figure shows the two-dimensional histogram of reflectivity, Ku band reflectivity, and Doppler velocity among different types. And above panel shows the for snow case, and bottom panel shows the rain case. In stratiform precipitation case, the distribution are concentrated compared to convective. And in convective precipitation, it shows a broad spread and indicating turbulent motion. And when we focus on the higher reflectivity area, higher reflectivity related to the faster falling speed. This may be due to the dense or large snow particles, especially in deep convective case, and especially in the tall deep convective case. And also bottom panel shows the rain case, and it has a clear relationship with Z and VD in stratiform case, but deep convective case shows more sparse distribution. Now we examine further this by compare this value with the DPR-derived particle size distribution. Now we calculated the particle force speed VTZ from DPM-DPR measurement. And in DPM-DPR level 2 algorithm, a drop size distribution estimated under assumption of gamma distribution to derive precipitation rate from radar reflectivity. And we in the algorithm, we estimate number concentration and mean diameter. From this observation, we can calculate terminal flow velocity like this, and the bottom panel shows the result of the calculation. And here, scattering cross section sigma b is calculated from assuming the spherical drops and falling velocity of the particle are assumed by the empirical relationship listed here. And this is the comparison between DPR Doppler velocity and terminal fall velocity calculated from DPR measurement. Upper panel shows the stratiform, bottom shows the convective. And the DPR calculated VTZ is broadly consistent with CPR measurement, and very consistent measurement shown. When we focus on the residual part, this may be related to the vertical air motion. And in stratiform case, it shows small variability. But in convective case, it become more scattered distribution as the K-band reflectivity gets larger. And this is the consistent result of the previously well-known characteristic of deep stratiform and convective precipitation. And this is the final part of my presentation. And my future work, I'm interested in such kind of vertical air motion is how related to the atmospheric diabatic heating. And the characteristics of vertical air motion in such kind of stratiform and convective systems are likely to reflect the latent heating from the precipitation and radiative heating associated with surrounding clouds. In some budget equations in large scale, Doppler vertical air motion is related to the radiative heating and latent heating rate. In previous GPM studies have attempted to infer the large-scale vertical motion from latent heating by estimating the latent heating dispersion from precipitation measurement. But now we can have EarthCARE have new measurements of vertical air motion, so we can investigate how this vertical air motion is consistent with the latent heating. And this is the one example of observation of coincidence dataset. On left-hand side shows the vertical air motion retrieved by the EarthCARE, and right-hand side shows the latent heating rate from GPM spectral latent heating algorithm, and it shows clear large heating in the convective case and associated vertical air motion. And on the right-hand side shows the stratiform heating and cooling below the 0° level. And it shows similar pattern we can see similar pattern in vertical air motion. And such kind of comparison I'm not trying, and I represent more in EGU and EarthCARE workshop at Oxford. And here's my summary. We investigated the vertical air motion inside a strategic precipitation system by using coincidence dataset of the EarthCARE and GPM, and the velocity from CPR can tell us information even in rain and heavy snow layers where clouds at reflectivity-only observations suffer from attenuation. And by combining these two measurements, we can get information about vertical air motion and particles. So this kind of result may provide new insight into global characteristics of them. Thank you very much.